Hello, everyone. In this video, we're going to be looking at an alternative measure for strength of evidence. We've already looked at the p-value as the measure of the strength of evidence, and today we'll be looking at what's called the standardized statistic. They both give us the same final conclusion about the measure of strength of evidence, so why do we have two? Well, sometimes it's easier to calculate one than the other, and sometimes a statistician will provide one, but maybe not the other, so it's good to be able to interpret both. Plus, the standardized statistic will give us a slightly different perspective on the situation, and so it can be nice to have two measures of strength of evidence to gain some little additional insight. So let's get into our alternative measure of strength of evidence. A quick comment, our key learning objective here is that we're continuing to learn to use the logic of statistical decision making. Deciding how strong our evidence is against a hypothesis will help us decide if we want to believe that hypothesis or not. So how do we measure strength of evidence? The process we've been using, we've called the 3S strategy. I encourage you to pause the video and see if you can remember what the 3 S's are right now. Right, statistic, simulation, and strength of evidence. We're going to be using the same first two S's, the statistic and a simulation, but then we will look at an alternative measure for strength of evidence. The one we have looked at is a p-value. I encourage you to pause the video and try to say this. What does the p-value tell us? Recall that the p-value is a probability. The probability of what? The probability of getting a result like we got in our data, or more extreme, assuming that the null hypothesis is actually the true hypothesis. So that's one way to measure how strong our evidence is against the null hypothesis. Another way to look at it is to look at how far off our statistic is, the result we got, from the mean indicated in the null hypothesis. And this mean, or we could say proportion, but it's actually the mean of the null distribution, is the number that we indicate in the null hypothesis. So we want to see how far off it is. We'll take a look at some images of that with the null distribution to get a sense of what we're talking about here. We standardize this calculation of how far off it is with respect to the spread of the null distribution, so we can examine how far off it is the same way in every study. So it's going to be called the standardized statistic. Standardized just means we calculate it in the same way so that no matter what study we're doing, we can use the same interpretation. So in order to understand this, we're going to have to understand a key measure of spread or variability, and that measure is called the standard deviation. Hopefully you've run into the standard deviation before and that this is a bit of a review, but it's really important to have a good sense of what standard deviation is telling us when we're trying to think about the standardized statistic that we're going to be using. So one of the key ideas about standard deviation is that it's measuring the spread in data, and that a higher number for standard deviation means more spread. It indicates the typical distance that data is from the mean of the data. So let's take a look at an example here. Here I've got a small set of values. The dots represent these different numbers here. And the standard deviation, which we indicate with the letter S, is 2.727. That means in this data, if I could find the center of it, which is just eyeballing it probably somewhere in here, the typical distance that my data is away from that is about 2.7. So if I went up about 2.7, down about 2.7, my data is typically somewhere in that range. And you can see we've got a lot of the data within that 2.727 of the mean of the data, roughly speaking. One key idea we said is that a higher standard deviation means more spread, and a lower standard deviation like 1.474 means less spread. And you can see this data still centered around the same spot, but much less spread out. So higher number, more spread, lower number, less spread. That's one of the key things to understand about standard deviation. Okay, so we'll be using that in our calculations here good little review there. Let's take a look at this example, deaths at St. George. Polaniki, Sismonides, Bland, and Jones in 2004 reported that the heart transplantations at St. George's in London had been suspended after a sudden spike in mortality rate. So they were doing heart transplants. All of a sudden, a bunch of people died after heart transplants, so they stopped doing them. Of the last 10 heart transplants, 80% had resulted in deaths. That's a terrible, terrible mortality rate. That means if you went to St. George's for a heart transplant, you are almost surely going to die. That's not a good thing. They compared this to a national average in all of Great Britain, and the national average for mortality after heart transplant was 15%. So you can see there's a very, very big difference there, right? And that difference is what we're going to try to examine as a way to talk about strength of evidence. We've talked about hypotheses before. Can you pause the video and try to write a null and alternative hypothesis for this scenario? Our null hypothesis is that the proportion of death, which we're going to call pi, is 15% at St. George, just like everywhere else in the nation. So we've talked about the null hypothesis representing the chance alone model before. Here, we don't really have a good sense of what's a random chance of dying after a heart transplant. So instead, we're basing our null hypothesis on what we might expect if St. George's is just like everywhere else. So sometimes we use the null hypothesis to do that kind of, to represent that kind of scenario. Is the typical thing that's out there happening also happening here in my scenario? So the null hypothesis is pi, the proportion of success, and here success is the thing we're looking for, which in this case is deaths. Pi is 15%. Alternatively, then, pi, and now here we need to think about, do we want to say greater than 15%, less than 15%, or just not equal to 15%? Well, they had seen a sudden spike in mortality rate, so it certainly seems reasonable to think that we want to test and find out if it's greater than 15%. It wouldn't make any sense to think that they had less than 15% going on in this scenario. All right, so there's our hypotheses. Here I have used the applet in order to generate what we call the null distribution. This is what we would expect to see the percent of deaths if the true percent of deaths at St. George's was 15%. So let's take a look at our three S's. Our statistic is 0.8 because we saw 80% of deaths in the last 10 at St. George's. Our simulation, we use the applet and we tell it, simulate the last 10 surgeries, give it a 15% chance of mortality, and then let's see how many times how many deaths we have in 10 surgeries. And so we can see 0 deaths showed up quite a few times, 10%, 20%. This is not surprising to see these low number of deaths if the true death rate is 15%, less and less as we get higher and higher. In fact, when we get up to 80% deaths, that never once occurred in our 10,000 repetitions to see 80% death if the true rate is 15%. So the p-value is 0. See if you can interpret the p-value. I encourage you to pause the video and try that. We would interpret the p-value this way. We'd say there is essentially a 0% chance of seeing 80% deaths after 10 surgeries or higher, assuming that the null hypothesis that the true percent of deaths is 15. So we'd essentially never see a result like we actually saw in our study if the null hypothesis is actually true. Another way to think about this is our alternative measure, which is if we have our 15% here, our null hypothesis value, 15%, 0.15, how far away is this result of 80%? And so we want to measure how far away that is relative to the variability in this data set. So how spread out is this data? We can measure that with the standard deviation. And then we're going to measure how far away, how many standard deviations away our result is. The general idea is that the farther away it is, the less likely it was to have occurred if the null hypothesis were true. The farther away it is, the stronger the evidence against the null hypothesis. So we're going to calculate what's called the standardized statistic. We use the letter Z to represent the standardized statistic in studies where we're looking at a proportion as our statistic. We will also use the letter T later on. But the same formula will work in all scenarios. We take our statistic and we subtract the mean of the null distribution. And then we take that calculation and we divide that by the standard deviation of the null distribution. So let's take a look at those numbers here. Our statistic, 80% deaths at St. George's. The mean of the null distribution, I'm going to just jump back one slide. That was this 15%. You can see it here. It was calculated as the mean. That came from the null hypothesis where we said the national average was 15%. So this is pi, the value from our null hypothesis. And of course, our statistic here is p hat. That's the symbol for our statistic. And then the standard deviation, 0.112, where did that come from? Well, we can see it here. The computer calculated it for us. It ran 10,000 simulations. It took all of that data and it calculated the standard deviation of those 10,000 results. So on the applet, you can check the little statistics box. It'll give you that standard deviation of the null distribution. And so we do that calculation and we get 5.8. So what is 5.8 telling us? It is what's called the standardized statistic. And a couple things to note. If Z is positive, then our statistic is higher than the claim of the null distribution. We have a positive number, positive 5.8. St. George's had more deaths than the national average. Not very surprising there, but the opposite is also true. Just take note, in some scenarios, we might see a negative Z. That would mean our statistic turned out lower than the null hypothesis claim. How about the number itself, 5.8? 5.8, our statistic is 5.8 standard deviations away from the claim. This indicates a couple of things. This indicates it is very different. Oh, excuse me, I'm having trouble drawing a straight line there. Very different from the null claim. What is maybe typical or not that strange to see? If we're about one standard deviation, that's very standard, right? If the deviation is about one, that's the standard. That's kind of normal. 2 standard deviations, now we're starting to see things that are kind of strange or rare. 3 standard deviations is very rare to see. 5.8 standard deviations is kind of crazy to see. So we're seeing something very different from the null claim. And that indicates that we have very strong evidence against that null claim. So if we try to claim St. George's has a 15% death rate, maybe that's what someone would say. They're trying to defend St. George's and say, no, they're just like the national average. We could see this and say, look, what's going on at St. George's is really, really different from 15%. Let me just show on the graph where this 5.8 comes from, and that might help you get a sense of this as well. So as I mentioned, we are trying to measure this distance from the null claim of 15% and the St. George's actual result of 80%. We said the standard deviations are about 0.11. So if I go up 0.11, 1, 2, 3, 4, 5, almost 6 of these standard deviation jumps, that's where that 5.8 standard deviations comes from. What would have been typical? To see something more like 1 to 2 standard deviations. If they would have had a death rate around, 0.20, 0.30, somewhere in there, we would have said, they're a little bit higher than national average, but not that crazy to see. When they got 5.8 standard deviations away, then we say, whoa, that is really, really different. That is very strong evidence against the null claim. So now if we're trying to decide between the two hypotheses, should we believe the null hypothesis? St. George's has a 15% death rate. No, we have strong evidence against that claim. And that's how we use the standardized statistic to make that decision. Just like with p-values, we had a little table that gave some guidelines for evaluating strength of evidence. Also for standardized statistic, we have some guidelines, and it'd be very good for you to get familiar with these cutoffs and how much evidence we tend to have. So if our standardized statistic is small, we have little to no evidence. If it's big, we have very strong evidence. I'm going to start at the bottom here. If we have a standardized statistic that's a really big negative number below -3, or a really big positive number above 3, we have very strong evidence. And that's what we saw at St. George's. We were well above 3, very strong evidence against that null hypothesis. If we are somewhere below -2 and above 2, but of course not beyond 3, then we have strong evidence against the null hypothesis. If we're below -1.5 or above 1.5, that's moderate evidence. And if we're between -1.5 and +1.5, we have little or no evidence. These are the same categories as the ones in the p-value, and pretty much they will line up with the p-value. So if you see a p-value that's below 0.01, 1%, you're also going to see a standardized statistic that's below -3 or above +3. So those two things will go hand in hand. Sometimes if it's a borderline case, if your p-value is right around 0.01 and your standardized statistic is right around 3, they might end up on one side, one on the other. So you might see a p-value that indicates strong evidence and a standardized statistic that indicates very strong. Both those scenarios are suggesting, hey, null hypothesis is probably not the true hypothesis. You'll never see like a standardized statistic above 3 and a p-value way up here somewhere. You may see them across the border sometimes, but usually they're always indicating the same thing for us. So you can actually choose which one you want to calculate and look at. We'll find that some scenarios it's easier to calculate one, and some scenarios it's easier to calculate the other. But you can actually use either one, and it's good to be able to interpret both. All right, so that's our, oh yeah, and I put them all on the same chart here as well. So that can be a real handy chart, and you should get real comfortable with all these values in the chart and the kind of evidence that they give us. So those are the main ways that we judge strength of evidence against the null hypothesis, which helps us make a decision about, are we going to believe the null hypothesis or the alternate hypothesis?